So in this video, I want to show you how to process and analyze your photosynthesis data using Microsoft Excel. And at the end of the video, what you should get is a sheet that looks a bit like this, with all your replicate data at the top, organized quite carefully, and also your rate calculations over here. An average rate calculation, which then goes into a graph that looks something like this. And the graph also has error bars that represent the variability in your data. Let's have a quick look at the sample data that we'll be playing with today. What you can see here is that this particular group has collected or is using the variable of distance from light. And so for their particular thing, this is a light globe. They have 3 treatment conditions, and all of these treatment conditions are a different distance from the light. One is 10, and one is 20, and the other one is 30 centimeters. Your treatments may involve exposing to different wavelengths, for example, red, green, and blue, maybe even UV. Maybe you have a 4th cuvette here, or maybe you have different concentrations of an inhibitor, or maybe you have a different kind of setup here, maybe intensity as well. The way that you analyze your data will be similar, as long as you have your data set up in a similar way to this, collected in terms of replicates at each treatment, and also absorbance measurements along a time series. So I've just taken this data and reformatted into this particular format here. What we can see here is that the data is essentially the same as before, but we've just organized differently. So instead of the times going across horizontally, we have the times going down vertically like this. You'll also note that my times, the minutes, are written just as the numbers 0, 2, 4, 6, and 8. Okay, not as 0 MIN or 2 MIN. Across the top here, we have our replicates. Okay, so the 10 centimeter treatment, we have 3 replicates, 20 we have 3, 30 we have 3, and for the supernatant negative control, this particular group has only done 1 replicate at each of the distances. So what we'll do first is we'll draw a really quick XY scatter graph in order to get a view of our data and see how the absorbance changes over time. Now, if we've set up our data in the right way, we can actually get Excel to draw a really quick XY scatter graph automatically for us. If we highlight our data, just a subset of our data here, okay, for example, the 10 centimeter treatment, come up here to the Insert tab. We want to insert an XY scatter graph here. So we click on this and we want the one with lines. So we'll select this and Excel nicely inserts a graph for us. Sometimes Excel doesn't guess that or it doesn't guess our data correctly, and it mixes up the X and the Y values, or it may mix your graph up entirely. But if you've set your data up the right way, sometimes Excel can guess it correctly like it has done here. So down in the X-axis, we have our times in minutes, and on the Y-axis, we have our absorbance. From this graph, what is really clear is that the change in absorbance is not linear over time. We see towards the end here how the change in absorbance is very, very slow, even though 4 minutes has elapsed since this point, also at this point. This is very different from initially in the reaction, where from this point to this point, over 2 minutes, there was a really big increase, or decrease, sorry, in absorbance. Now, the reason for this is because the substrate may be running out. So, for example, if you have DCP-IP, which is oxidized, and it is being turned into DCP-IP reduced over time. If you have DCP-IP oxidized running low, which is occurring from here onwards, then this reaction is going to be slowing down, which is what you observe from 4 to 8 minutes in this particular setup of the 10 centimeters treatment. What this means for us is that if we're trying to work out the rate, it is inaccurate for us to work out the rate from this point to this point. Because if we did that, then our rate calculation would look something like this. What we should instead be looking at is we should be looking at the rate where the reaction is still linear. Okay, so for example, for that point, and that point over there. You see the gradient of this particular line here is very different from the gradient of these 3 lines here. Therefore, these 3 are accurate, and this one is inaccurate. Let's consider how this looks for our other treatments. What we can do is we can select the graph in Excel. When we select it, the data that is going into the graph should be highlighted. What you can do then is if you move your cursor to the edge of this rectangle, you see how the cursor changes from a fat plus to an arrow with a moving cursor there. What you can do is you can click and drag this along, and Excel will update the graph based on the data that you select to plot. And so, for example, what we're seeing here is in the 20 centimeter treatment, we have a different linearity. So, for example, this particular graph here is linear, perhaps from 0 to 6 minutes in all the 3 replicates, maybe except for test number 3. This other replicate, it looks like it is linear all the way until 0 to 6. And so we can probably say that the linear range is between 0 and 6 minutes, which is different from before for the 10 centimeter, where the linear range was only between 0 and 2 minutes. So, how do we get Excel to work out the rate for us? There are 2 ways to work out rate. One way is to literally take, for example, the absorbance at this point, take the absorbance at this point, and essentially do a rise over run calculation here. What that looks like in Excel is something like this. So if we try to work out the rate, for example, for test number 1, what we can do is we can say, we can click in this cell here and press the equals button. When you press the equals button in Excel, it tells Excel to actually work something out mathematically. So we can say, well, this should be equal to the absorbance at this point, okay, which is at 6 minutes. And so we can click into this cell here, minus the absorbance in the beginning. And then we need to divide that by the time difference, which is 6 minutes here. Now remember, mathematical operations apply in Excel too, and so you need to make sure you have brackets here, otherwise the division will occur before the subtraction. And so here we have the rate. Now what we can do in Excel is that if we're happy with this calculation, we can actually click and drag this across. You see how my cursor changes when I click or when I hover it over this bottom right hand corner. I can click and drag with my mouse, and Excel will populate this formula that I've drawn up here, and it will populate this to the right towards where I've dragged. Now this is quite a simple way of calculating rate. But the problem with this way of calculating rate is that it only really takes into consideration 2 data points. It takes into consideration this first data point here, and also takes into consideration the second data point over here. It ignores basically the data points in the middle. And so we can actually use a different function of Excel to work out the rate for us, essentially calculating a trend line, a mathematical trend line, between or considering all these points. Okay? And so we can essentially ask Excel to work out for us what the slope of this particular line is. Okay? So the function that we're going to be using is actually called the slope function, funnily enough. So the slope function in Excel allows us to work out, or get Excel to work out this slope for us, the gradient of this line essentially. So how do we get Excel to work out this function, the slope function for us? Well, let's put a new row here and let's call it the smarter rate. That's kind of a weird name for it, but let's stick with it for the time being. Okay, so we'll click into this cell here, start with the equal sign because we're getting Excel to work something out mathematically for us. The function's name is SLOPE, so I'll type it on my keyboard. And then what you see here when you start the brackets up is that Excel is now asking in bold for the known Y values, followed by a comma, followed by the known X values. Our known Y values here are the absorbance readings, and our known X values here are our time readings. Therefore, in order to work out the slope or the gradient for this particular bracket here, we need to take all the absorbances from 0.01 all the way down to this 6-minute reading here at 0.468. So to do that, we can click and drag with our mouse, and then we type the comma using our keyboard, and then it's asking for the known x's now, which is essentially 0 to 6. Close the parentheses, press enter, and Excel has now worked out the slope for us, considering all the 4 data points from 0, 2, 4, and 6 minutes. What we can do is now we can click and drag this over, and what Excel has done is essentially copied our function over. The problem here is that as Excel is copying the function over, it's updated the references to the cells. sometimes it doesn't do this the right way if we don't tell it to. And so what you see here is that even though it's correctly moved the blue box over here to test number 3, replicate number 3, we did not want the red box here to move. We want the red box to stay in the minutes. So what we can do is we can come back here and just click and drag it back, and we're all good. Again, going over here, Excel has updated the blue, updated the red as well. We want the red to be back here, and so we'll click and drag and put it back there. There's another way to make Excel fix these particular values, but that's for another video some other day. So what you can see here is that using more data points by calculating ways the slope using the slope function, Excel has actually given us a slightly different rate to our easy way up here. And so really, calculating rate using our smarter rate or using the slope function is actually much better. So how about we go ahead and delete these? We don't need them anymore. Okay, so for our 10 centimeter treatment, also our 30 centimeter treatment, what I'm going to do is now I'm going to calculate the rate also for these treatments quickly. So if I click on this graph again, I can move this data selection around such that again I can get the plot showing me where the linear rate exists. And so for 10 centimeters, for example, the linear rate is between 0 and 2. And so what I'll do here is, again, I'll use equals slope, start the brackets up. The known y values now are only these two, and the known x values are these two as well. Press enter, select that, and then I'll drag across, go into here, and then update these references here. So I'm going to do the same thing for the 30 centimeter treatment over here, and over here what I see is that the linear rate essentially extends from 0 to 8 minutes. And so what I can do is I can do equals slope, select the y values, select the x values, close the brackets, and then drag across. Let's have a look at our supernatant. So again, if I click into the graph, drag the data over here, we see that in the supernatant, it's fairly static, sitting around 0.9-ish, down 0.8 maybe, but again, the rate is fairly linear throughout the whole 8 minutes. And so again, what I can do is I might as well click this, drag that across, and Excel will be able to populate my formula for me. I'll just fix up all of these. And so now I have the rate calculated using the slope function. Let's change this back to rate, which is, the units are essentially absorbance per minute. Now that we have our rate calculations for each of our replicates, we don't actually need this graph anymore. And so let's delete this one. Instead, what we need is, we actually need representation of the average rate. And so we need to find the average of these, put it somewhere, the average of these, put it somewhere, and the average of these, and put it somewhere too. So what I might do is I might start up a new subtable within my sheet here, and it might contain something called average rate. And we'll have one at 10 centimeters, one at 20 centimeters, and one at 30 centimeters. I'll just shift this down, give me a bit more space. Okay, so these three can be for the chloroplast isolate. In order to merge these three cells together, I can come up here to the toolbar and click this button here and merge in the center. We call those a chloroplast isolate. I'm going to do the same here. I might copy these three over and merge these three and call that the supernatant. Okay, I'm just going to try to center these to make it a bit prettier. There we go. Okay. So now what we want to do is we want to find the average of these three and put it down here. Find the average of these three and put it down here. In order to get Excel to work this out for us, again, use Excel as a mathematical calculation tool, very powerful that way. We can do the equal sign, okay, and Excel has a function called the average function. And so we can literally type average, start the brackets up, and then we can select the values we want to find the average for, close the brackets, hit enter, and Excel has worked out the average. And then we'll just keep doing that for our 20 and also for our 30 centimeters. Now, because for the supernatants, this particular group did not have replicates, what we can do is we just get Excel to use those values. So simply we can click into this cell here, press equals, click up here, and press enter. This will make this cell equal to this cell over here. Again, we can click and drag, and just double check Excel's on the right thing, click into this cell, and make sure Excel is referring to that particular cell there. Now, the whole point of doing replication in scientific research is to actually find out the variability in your data. One representation of variability is a thing called standard error. Another one is called standard deviation. Standard deviation is a bit easier to calculate, so we might start with that. So let's start a new row here called standard deviation. Again, Excel has a function that can work this out for us. Just like the slope and the average functions, we have a standard deviation function, which is typed in as STDEV. So again, if we start the brackets up, we can find the standard deviation of these three values. We highlight those with our mouse, close the parentheses, and click enter. Again, let's do that for our 20 and our 30 centimeter treatments as well. Because our supernatant has no replicates, we can't actually work out a standard deviation for those particular values. So now that we have our averages over here, let's get Excel to draw a chart for us. If we formatted our data in a particular way, Excel can typically draw a very nice, or have a very good guess at the chart to draw for us. To insert the chart, we'll go to the Insert menu here, Insert tab, click on the Insert Column Chart button, and then we'll select a very basic 2D column chart. You can see that this particular chart shows rates along the y-axis as well as the different treatments along the x-axis. In this particular chart, the x-axis labels are a bit mispositioned, and so what we might do is we might right-click on them, select the Format Axis option, scroll down over here to Labels, and then we might position this high up above the chart. If you're using a different version of Excel, this menu over here on the right may appear as a separate dialog box. There are some other minor formatting issues with this graph, so let's fix them up now. Figures in scientific writing don't have chart titles, and so let's select that title and delete it. The other thing here is that we want to have actually a line along here. And so to add that line, we can click on this axis, right-click on it, format the axis, and we can come over here to the paint bucket, and then for line, we want actually a solid line or an automatic line. Now the color should be light gray, just like the rest of the graph. So we see that now we have a solid line there. Horizontal grid lines are not too necessary, and so to get rid of them, what we can do is we can select them and then press delete. So what we have now is we have the averages plotted on this graph, but let's actually specify the title of this particular axis. And so our y-axis actually represents the average rate, and so what we can do is let's add, by clicking this plus button over here, an axis title. We don't really need an x-axis title because it's already given for us, but let's add a vertical axis title. To change it, just double click into this box here and let's call it something. This can be the rate of change of absorbance. It is the average rates of absorbance change per minute. Now, because our graph shows the average rate of change, we also need a representation of the error or the variability in our data. And so we can actually add error bars to represent the variability. Let's close down this format shape dialog. In order to add error bars, what we can do is we actually need Excel to plot these values as the plus and the minus error bars. To get Excel to do that, you click onto your columns itself. Let's maneuver this around a little bit. Click on the columns themselves, go to the plus. Again, this may look different if you're using a different version of Excel. Go over here to error bars, and what we want to do is we want to add a more options error bar. This is because Excel isn't very good at actually working out the standard error, percentage, or standard deviation for us because it doesn't know about our data. So go into more options. And what you see here is Excel is plotting both the plus and the minus error bars, which is great, and also it's putting a cap on the error bars, which is good too. We need to come down here and get Excel to use a custom value for our error, because we've already calculated this in the standard deviation. So to get Excel to use our standard deviation calculations, we come down here, click custom, and then we have to select specify value. We want Excel to plot the plus standard deviation, also the minus standard deviation. And so here in the positive error value, we'll delete the current or the existing values here, and then we'll highlight the standard deviation. We can actually highlight along the entire way, even though there's no values there. For the negative error values, again, we delete what's existing in there. We can highlight along the entire row, click OK. And what you see Excel has done is it's plotted the error bars, which are indicating plus and also minus the standard deviation. There's no error bars plotted here for the supernatant because there's no values along here, because obviously there were no replicates done for the supernatant control. So there we have it. We've taken our raw data, which has been formatted a particular way. We've worked out our rate using the slope function, and then we've taken the average of these rates, calculated their standard deviation, and then we've drawn this onto a column chart. Now just one last quick note about how our particular column chart looks. Some people have issues with how the column chart actually goes into the negative. Going into the negative is perfectly fine in our situation here, because what we're looking at in our chart is the average change. And so if the average change is negative, what this is saying to us is that over time, we have time here and absorbance here, and we have a negative change. It means that all it means is that the absorbance is decreasing over time. And that's exactly what we saw. And so remember, negative doesn't always mean bad. It's just negative is a different way of representing our data. Okay, so a negative change here means that the absorbance is decreasing over time. In the 10 centimeter treatment, which is very close to the light, we have a very, I guess, highly negative reading. For our 20 centimeter, it's less negative, and for our 30 centimeters, it's less negative. This makes sense because at 10 centimeters, it's very bright, and so you expect this to have the most decrease or the most negative change. And at 30 centimeters, you expect the least negative change or the least decrease. In the supernatant here, what we have is we have not much decrease at all. Okay, so this negative control worked out quite well. So thanks for watching this video. Hopefully it was helpful in helping you to analyze and process your photosynthesis data.